All right, hello. Can everyone hear me? Raise your hands if you can hear me. Okay, good. Just want to make sure that I get everyone in the back, because this room is pretty deep, as you might have noticed, and so I want to make sure that you guys can hear me. Welcome, everyone, to Data 100, summer of 2019. My name is Sam, and I'm the instructor for this class this summer. And I'm going to do like a full intro of myself, as well as my course staff later on in this lecture. But for now, let's move on to some interesting tidbits. Okay, so an announcement for today, and probably for like the first few weeks of the class, is if you ask a question during class, then please remember to start with, "Hi, my name is so-and-so. Hi, my name is Sam. Here's my question," and then ask a question. That way I can get the names of people who ask questions in class and just try to get to know you guys a little bit better. When Data 100 is taught during the semester, it's a class of like 800 students now. And so there's like no way for an instructor to know everyone in the class, all the names of people in the class. Since our class in the summer is relatively small by Berkeley standards, at only 140 students, I will try to remember your names, although you will have to forgive me if I can't do it. Okay, so in today's lecture, my goal is mostly to entertain you. And I'm going to entertain you by trying to give you some context about why data science is interesting, why data science is useful, and why data science might be a bit scary. I will cut in the middle to talk about some course logistics, and then at the end of the class, for the remaining 1/3 of the class, I'm going to do some review of sampling and probability, concepts that you should have learned from Data 8 or an equivalent class before taking 100. Okay, so I'm going to do some interesting stuff, some logistical stuff, and then some interesting stuff in the end, so it'll be like an interesting sandwich, hopefully. Okay, so what's with all the hype around data science? Well, one reason why the words data science might be kind of taking hold in people's minds these days is because of the data explosion. So in 2010, it was estimated that the world used about 1.6 zettabytes of data. And in 2013, that number tripled to 4.4 zettabytes. Now, a zettabyte is like 1 trillion terabytes, okay? And a terabyte is about like the hard disk size of a personal computer these days. And so you can roughly estimate these numbers as a zettabyte being the equivalent of every person in the world using 100 computers worth of data and just filling up all the hard disk space with all the data they used / is stored about them. Now in 2013, this number was 4.4 zettabytes, which corresponds to about 440 like personal computers, per person in the world. And in 2019 and in 2020, that number has skyrocketed to 44 zettabytes. And that's, you can think of just like, as you've gone older, every year, you're just like piling up your data into these computers, all your YouTube videos, all your chats with your friends on like your online messaging things, all the homework that you did. And even though your activities may be roughly the same, the amount of data that you use and the amount of data that's being collected about you is increasing at a tremendous rate because everyone these days is interested in getting more data about you. Where is this data being stored? A long time ago, this data was being stored in physical form. So it was like recorded in some logbook somewhere and like stashed in like someone's desk or like stashed in a library. But these days, most data is stored digitally in data centers all around the world, like this one at Google. Basically, many companies or many organizations have like tons of these like server racks and whatever, and they just like store tons and tons of data about everything they can possibly get their hands on. And the difference between then and now is that although perhaps like the physical like size of these machines or the physical size of those bookshelves has not changed too much, the amount of data has increased a lot and the access to data has increased a lot. The difference between going to a library and perhaps like reading a book on your Kindle is that you can download a book on your Kindle from anywhere in the world and access it very quickly. Whereas to go to a library to access a book, you have to drive all the way there or walk all the way there and then like go find your book in the bookshelf and then like take out the book and then read it. These days, you can get access to most data sets, most publicly available data sets, not by going to some lab and like visiting them and asking them for permission and then like copying over the data into your handbook. You can do it by going to their website and downloading the data and just accessing it right away. And of course, that means that data is much easier to store, it is much easier to access, and it's much easier to copy. And so you may ask, like, well, what are some of the implications of all this data? And you may ask the question, well, who is this data? The data is increasingly about you. Last year, Facebook was breached by Cambridge Analytica, and they found out that like 187 million people's Facebook accounts were breached. I think mine was included in that. I'm not sure. I hope my friends didn't play that like dumb. I forget what game it was, but it was like if you played a game, if your friend played a game, this company would get all the information about you. And increasingly, because of the access to data, and because people are not super careful about protecting your data, data is just kind of getting everywhere. And once it's out there, it never really disappears. Once companies have access to your data, they pretty much keep it forever. Well, we've asked where is data, and we've asked who is data, and in the words of Jax, we may also ask why is data. And if data is kind of the scary thing that we see in this news all the time, why are people still so interested in it? The reason is because data is actually useful. Despite its ability to be used for nefarious purposes, we in this class want to use it for perhaps more noble and more interesting reasons. You may have heard of these recent news from science, where scientists recently discovered gravitational waves. And even though you may not know what gravitational waves are, what you should know is that to actually detect these waves, because they're so small and so faint, they had to build like multiple large-scale detection centers all across the world. And then when one lab gets like the signal of a wave, all the other labs like rush to like fill in and try to say, okay, we also got the same signal, and like they combine their data together. And in effect, there's no way to detect a gravitational wave because it's so faint with just one lab. And so in order to actually say that, we think that we found something important, you have to combine many data sources in a number of interesting ways. You may have also heard of this more recent news of scientists recently capturing an image of a black hole. In order to make this happen, so actually the interesting thing about the black hole is that in order to actually take this screenshot of a black hole, because black holes are so small, if you wanted to build one telescope to do it, you need the telescope to be the size of the Earth, which is not that practical to do. Instead, what scientists did was they sent out multiple satellites all across the world and set them up in Earth's orbit, and then they all kind of aimed the same spot. They took a picture, and then they computationally reconstructed this picture based on the very, very, very faint signal they got from each of those satellite telescopes. And that also is a data science problem. In industry, people use data science to make things more efficient all the time. For example, UPS recently used some routing optimization software and some tracking on where people go and how many packages are in the cars and how much mileage each truck gets in order to reduce the number of miles driven by 100 million. One interesting result that UPS decided to do is that they never turned left. So it turns out that turning left is a waste of gas and a waste of time for these drivers. I don't know if I'll stop turning left because Berkeley traffic is atrocious, but you might keep it in mind as something that UPS did based on some data. Another way that data is used is in search engines. For example, if you're programming a search engine, you may ask the question, well, how do I give people the results they want to look for? How do I distinguish between, if a person types in splash zone, how do I make sure to show them water park things? Versus if a person types in friend zone, it's not an actual physical zone of friends. It's some metaphorical, friend zone. And you may also ask the question, well, what if the person types in frozone? That's not a thing or a metaphorical thing. It's actually a reference to a superhero from a movie. To actually make this happen, Google uses all sorts of data techniques, and they look at the behavior of people searching and what people click on in order to decide algorithmically, using data science, what results to show you and why and how those results might be useful to you. So data science, as we define it in this class, is the application of data-centric, computational, and inferential thinking to understand the world, like take pictures of a black hole, or solve some problems, like give you some good search results. Because it's new and because it requires many different skills from many different fields, data science is fundamentally interdisciplinary. That's why it's cross-listed between CS and stats in Berkeley. And that's why in the future, when you go on to use data science and real-world applications, you'll probably be talking with people from all sorts of walks of life. And even in the classes in Berkeley, you'll notice that there's a wide variety of students who take these classes. I believe Data 8, our freshman-level data science class, has over 40 unique majors, like distinct majors. And because of that, I think the data science classes are pretty interesting to teach and also pretty interesting to be a student. As a kind of hand-wavy approximation to what data science involves, you may have also seen this famous Venn diagram that Drew Conway made in 2010, which essentially says that data science is like the intersection of hacking skills like computing or programming knowledge with some math and statistics knowledge, with some domain expertise or some substantive expertise. This diagram has undergone like some hot debate since 2010, and people have like made 4 bubble Venn diagrams and like 5 bubble Venn diagrams, and no one can really agree on what exactly constitutes data science. But I hope to show you in this class that even with that, regardless of how you define it, if you have some basic skills, you can find some interesting insights from your data. So in this class, what we want to do is prepare you for some more advanced classes. This class is not kind of like the end-all be-all of data science, although one of the reasons it was originally designed was to take people who have taken some computing classes and some stats classes and get them ready to interview for data science positions. I don't know if this class will get you all the way there, but it'll get you part of the way there at least, because a lot of the concepts we talk about in this class are concepts that data scientists use in their day-to-day lives. We also want to prepare you for some future classes at Berkeley or at your own universities if you're visiting us from another university. Data 100 is a good class to take before taking a more advanced machine learning class, a more advanced like databases class or a systems class. And so we want to give you some context, some reasons, some motivation, and just trying to give you a broad survey of all the different things, or perhaps some of the different things that we use in data science. In this class, we'll work with real data. We'll work with data sets collected from the real world. We won't synthesize the data for you. Instead, we'll tell you where we got the data and why it was collected. We'll use the tools that people use in their day-to-day jobs, like pandas and SQL. And we'll also teach you the techniques that are still in use today, like regression and modeling. And all in all, we want you to be able to kind of combine these two approaches of being able to program, being able to think computationally, as well as being able to think more broadly. How do my results generalize? And what can I infer about the world from what I do in my analysis? To give you a sense of the breadth and the applications of data science, I just have here a list of questions that you can attempt or at least approach from a data science angle. The COMPASS algorithm is an algorithm used to determine whether a person convicted of a crime is likely to be convicted again. It was famous for being proposed and perhaps used in some courts, and it's an example of, and you'll talk about this in discussion today, I believe. It's an example of an algorithm being used to make decisions about humans, which raises some questions about how these algorithms work. Who will win the election? Where should we put our bikes? What should we eat? What about this herbicide that people got into a big lawsuit over? What about people coming into our country? How do they affect the economy? And I have a question for you. So suppose you had a list containing the first names of everyone in class today. What might you find out from this data? Let's take a look. And I have here a demo. So, pull this up. Okay. Can you guys see this text in the back? You don't really have to see this text for today's lecture, but I do want to make sure that I kind of calibrate the settings here correctly. All right, what about now? How is that? What about now? Okay, a little better? Okay. Well, for today's lecture, you don't have to know the code that I'm writing, but in the future, I will be typing things into this notebook as I teach. And I think as alternative for people in the back, I'll try to post a notebook I'll post a notebook I'll use in class ahead of time, so you can kind of take a look at that in case you can't see the screen. But just for today, for good measure, I will zoom in one more time. Hopefully it doesn't break too much things. And if you're in the back and you really can't see, you may want to consider like moving up to the front in future lectures so you can kind of see the code that I'm writing here. It's also kind of hard because the screen is really small. As you can see, our regular screen is like 4 times the size. And so I will do my best today. And luckily, you don't have to actually know the code that I'm writing. I'll just talk through it and tell you kind of like mentally what I was thinking about as I was working on this problem. Okay. So what I'm going to do is take the list of the names of everyone in this class. I will show you that list here. And what this is a data table. This should be familiar to you if you've taken Data 8. What I want to do to this data table is I noticed that there's some capitalization of names, but I'm not sure if this capitalization is consistent. So what I'll do is I'll just lowercase all the names in my table. So I have here a table. I've only shown the first 5 rows of it, but there are actually 138 students when I download the roster for this particular table, and this just contains all the first names of everyone in this class. For FERPA and privacy reasons, I won't show the whole table because I think there might be some rare names, but I did check to see whether these names were used, and I don't think that people will stalk you based on your first names here. Okay. So there are 138 students on the roster. And if you look at the second column here, we see that there's a column that says enrolled. And we might ask, what's actually in that column? And running some code can tell us quickly that there are 132 students enrolled and 6 on the wait list. This number has changed since then, but the numbers have stayed roughly the same since then. So this roster contains both the students that are enrolled in the class and the students that are on the wait list for the class. We might also plot, the distribution of named links. So what we'll do is we'll take the links of the names of everyone in class and put them on a histogram to see how long people's names are. And from this plot, we can see that most people have a name between maybe like 4 to 8 characters long. We can also see that if we had some weird names, like people who had a name of 1 character long, that they would show up here. And if someone has a name of like 100 characters long, they would show up way down here in the tail end of this histogram. So being able to see this histogram gives us a quick way to see, okay, my data look pretty reasonable, or at least like I don't have some crazy names, and I might have like messed up my data analysis somewhere. Okay, so with just a list of names, this is roughly all we can do. But we can ask some more interesting questions if we bring in some data from outside. And in this case, what I'm going to do is take a look at one name in my data table. This name is Andrew. And we might ask the question, well, what might be able to find out from this name? One thing we might be able to find out is the sex of this person. So was this person born male or female? That might be correlated in some sense with the actual names that were given, because some names are generally given to guys and some names are generally given to girls. There are also other things we might find out, but let's start there and see where we go. What I'm going to do is read in a data table containing the counts of names registered in the US Social Security database from 1880 onward to 2018. You can see here that there's someone with the name Zizix. I don't know how to pronounce it. I don't think there's anyone named Zizix in this class, so I don't apologize for pronouncing your name wrong, but this is being recorded, so hopefully like the Zizix doesn't come find me and hunt me down. But what they did here is that they just recorded, when people are born in the United States, the government records their name. And this data set just counts up all the names that were born in each year, the sex of the baby, the name of the baby, and how many of those names were given to each baby in every year, okay? So we have here, for example, the name Mary. There were 7,000 Marys born in 1880. There were 5 Zairees born in 2018, so on and so forth. Okay, so this table has almost 2 million rows. All right, so here's some more data. And we can see here that this data is a 100% sample of records. on Social Security card applications as of March 2017. I should update this to 2019. There we go. All right, so this contains everybody. This is everybody in the US if you're born and you got your name registered by the government. Okay, so here's something we might do. We might plot the number of babies born of each sex between 1880 and 2019, or 2018 in this case. We can see here that there's a pattern in this plot, and we might ask why this pattern came about. So for example, there's very few babies here, and then all of a sudden there's a spike. There's a dip here, and then another spike here, and a dip here. Why do you think this might have happened in the far left? Why do you think, well, it looks like there are like 0 babies born in like 1890, right? Why do you think that's the case? The war? Okay.
Data wasn't so accessible to people.
Data wasn't so accessible to people? Okay, one more suggestion?
The gold crisis.
The gold crisis?
Yeah, there was an inflation crisis that caused the depression in the 1890s.
And very interesting, yeah. So there's like a country level crisis. There could have been like, I don't know, like maybe the government just told everyone to stop having babies for like 10 years. We can actually find out by going back to the data description and find out that many people born before 1937 never applied for a Social Security card because Social Security didn't exist until somewhere around the early 1900s. And so they kind of backdated this data, and because of that, there are some people here that are missing, right? So there are many reasons for patterns in the data. Some of them you may guess and get right, but other times you may guess and get wrong. Okay. What about this spike right here and then the corresponding dip here? Why might this have happened? Anyone have any guesses here? Sorry, Siri. Yeah, sure. There was a war. World War II? Sounds like an important war. Also a depression, yeah, so a lot of stuff going on in America at that time. It's not a good time to be an American, I guess. Yeah, so that might have happened. What about the spike here in 1950?
A baby boomer, so the post-war spike.
Yeah, so people got back from the war and they were like, let's make babies. And so they got together and had a lot of babies in 1950s to 1960s. And it's kind of leveled out since then, and we can see that the numbers here, it was like a spike, and then it kind of dipped down and kind of leveled out. There are many reasons for this. We won't speculate too much, but these are the questions or the proposals that you have are also proposals that can be answered by looking at data. I just don't have the data with me. But you could, if you wanted to, find out reasons for these patterns in the data by getting more data. All right, so we looked at that plot. Let's keep going. So what I want to do here is take a look at the names in this table. I lowercase them because I'm just working with all lowercase names at this point. And what I can do is look at the names of people in this class. All right, what I can do is look at the names of people in this table and try to figure out whether a name is more likely to be given to a baby born a male or a baby born a female, right? So for example, if I notice that there are a lot of female babies born Mary, but not a lot of male babies born as Mary, then the name Mary is probably given more to females. So I'm going to do that right now by writing some code. And this code uses pandas, a library that we'll be introducing tomorrow and the rest of this week. And we can see here that in this table, what we've done is made what's called a pivot table. You may remember from data 8, where we have the row containing the person's name, as well as a number of people that were given that name for each sex. So for example, Aban was given to 114 males and 0 females. So if a person in this class is named Aban, I would pretty much guess that you're a male. What we can do is we can apply the same logic to everyone in this class. So I'm going to do that, and then I'm going to apply this logic to everyone in this class. And we can see here, what I'm going to do is I'm going to say, okay, I'm going to find the proportion of babies that were born female for a particular name. And if that proportion is greater than 0.5, then I'm going to say you're probably a female. You're more likely to be female than not a female. And if it's less than 0.5, I'm going to say you're more likely to be a male than a female. Okay? So we can see here that I made a function to do that for me. And when I type in my name here, it says that I'm probably a male, which I am. One interesting thing that I wish I could, does this work? Okay, great. So I can show you this, which is a little bit of UI, a little bit of notebook magic, that lets me type in a box and see what name gets predicted out. So for example, if I write Sam and add Sammy at the end, it still says male. If I change this to Samantha, I believe that turns into female. If I type in Joe, Joe is female. But if I type in Jose, it's male. Joseph is male, but Josephine is female. So you can see here that from this data, and this kind of corresponds to your intuition about names, right? Just based on your own personal experience. And we can see that we can use this data to do, in a principled way, some sort of prediction or some sort of inference about some characteristic of a person's name. Anyone want to try their own name? Serena? Looks like you're probably a female. Sorry, Serena. Yes?
Sorry, Peyton.
Peyton?
P-A-Y-T-O-N.
Peyton. P-A-Y-T-O-N. Looks like it was more likely to be female. Not bad, not bad. So I'm 1 for 2. 1 for 2. Okay, well this is a very simple thing to do. So I'm not surprised that we're getting stuff wrong. You may ask the question, how might we do better? I'll leave that as a question for the listener. Okay. So what I'm going to do is apply this prediction to every name in my data set. All right? And so for every name in this class, I should do that head, I predicted whether this name belongs to a male or a female. And what I can do is now take a look at the distribution of sex in this class. It looks like I predict that there are about 33 females in this class and 63 males and 42 questionable people. And I suspect that people's names are questionable, for example, because in the summer we get a lot of international visitors who are coming from some other country. And because of that, their names aren't registered in the US government, and their names are probably not in this data set. All right, so why don't we try it out? How many of you guys are male? Okay, take a look around. I'm not going to count. I'm just kind of estimate, like ballpark estimate with your eyes. How many of you guys are female or identify as female? Roughly like I don't know, 1/3 to 2/3. Okay, how many of you guys are from another country or visiting us from another country? How many of you guys are born in another country? Let's see, or have like a. Okay. I don't know how well we did, but you know. Kind of ballpark estimates. All right, so let's go now to, let's look at now, we know that in this table that we originally had, we had the name and the sex of the baby, the number of babies born, and the year. And with this year, we can do some other estimation. What we can do is we can say, okay, well, if the name, Beyonce was not popular in 2000, but suddenly became really popular in 2001, then we can kind of get an estimate for a person's age if their name was, say, Beyonce, right? And so what I can do here is use this year column to estimate the ages of people in this class. The logic works roughly the same way, where I will look at this table, look at the name, and for each name, I will look at the average year of birth. So what I'm doing here is I'm saying, okay, well, Abans were born mostly roughly in like year 2013. Abhaz were born in like year 2013. It looks like a lot of these names are pretty recent because they're like at the beginning and the end of the alphabet. So you get some kind of wacky names down here. If your name is Zizix, it looks like I would estimate you're like 5 years old. So congratulations for being 5. Okay. I can also do the same thing as I did before, where I can take a person's name and estimate their age from it. In this case, I have the name Fernando. It looks like Fernando was born, or I would estimate Fernando was born in 1988. If I type in my name, it looks like I'm pretty old, it's 1941. Anyone else want to try their name? Sure.
Colby, C-O-B-Y.
Colby. Hello, Colby. Is that close? How? 1 year off. Wow, amazing. Anyone else want to try?
Can you try your Game of Thrones name just to see
Yeah, I actually have something like that at the very end. Good question. Oh.
Like Tyron, for example.
Tyron?
Yeah. Tyrion, sorry.
Tyrion. 2011. Looks like it was pretty recent. Looks like someone watched Game of Thrones, someone's like, wow, Tyrion would be a great name for my kid. Okay, so what I'm going to do is use this to make a prediction for everyone in this class. Okay, so I have here our table, do that. Okay, and I'm going to plot the distribution. And this is my predicted distribution of all your names, like based of your ages, just based on your name alone. Okay, so it looks like I have here a curve. Some of you guys look pretty old, some of you guys look pretty young, but it looks like maybe like the peaks are around like 1990, 2000, which hopefully is quite right. Unfortunately, what happens when I do this is when I take the average year, I get something kind of weird, like 1987. So it looks like I would predict that the average age of the class is something like, oh my gosh, is that like 30 years, 32 years? 32 years, and I think most of you guys, or most people taking data 100 in the past have been younger than 32 years old. And so you might ask the question, well, what happened here? Why might this be inaccurate? Any guesses? Sure.
The outliers.
Sorry?
The outliers.
The outliers, yes. Yeah, because we're taking the average, it's a good insight. We're taking the average, and so outliers in our data set kind of drag our average down. Yes? Yes?
It has been collected since 18 or 50 or something, so there will be a lot of people.
Yeah, that's a good insight too, where since we collected data for many years, and names have presumably been around for quite some time, most names have been around for quite some time, most names will look old, because, for example, if you're named John, I think John was popular in like 1950 or something, so we'll probably predict your age as like being 60 if your name is John, even though you might clearly not be 60. Okay, these are some good guesses, and we can take a look at what's happening here by looking at the frequency of John over time, and we can see here that John was pretty popular in 1920, especially popular in 1950. But since then, it's kind of fallen out of style, and it's kind of gone down in time. So if you're named John, I would probably guess that you're pretty old. Even though if you're in this class, I might guess that you're probably pretty young. And so there are ways of kind of combining statistically like different ideas or different like prior information, combined together different information sources in order to decide on a prediction. But in this case, since we're doing something really simple, our predictions are also quite simplistic. We might also look at a name like Kanye. Let's look at the name Kanye. And we can see here that Kanye had no one. Kanye was like never given to any babies until like, 2003. And everyone loved Kanye. But now he's kind of dropped in popularity, so no one wants to name their kid Kanye. I guess they love the old Kanye. Okay. All right. We can also look at the name Siri. And what I have here is I've plotted the name frequency of Siri over time, and at this red line, can anyone guess why I drew this red line here?
Siri was bad.
Yep, yeah. So this is the year that Siri was invented, and so it looks like Siri was on the rise. It was gaining some popularity in America, and then Apple released Siri, and everyone instantly just stopped naming their baby Siri, because they didn't want the baby to be confused with their virtual assistant. All right. There are some interesting patterns in other names too. Like the name Hillary, for example, was not popular until about it got really popular until 1980, 1990, and then it plummeted. Why might it have plummeted? Any guesses here? Yeah. Yeah, so, sorry, Bill. Sorry, Hillary. It looks like because of your actions, the name Hillary isn't as popular in the US anymore. Okay. All right, so that's the end of my demo. Are there any questions here? Did someone want to try out Game of Thrones name? Tyrion? Let's try Tyrion. Let's do that. Yes, indeed. I don't know the years when Game of Thrones was popular or released, but it looks like, well, his name went from like 10 to like 60, so that's a pretty good jump. Any other names you want to try? Khaleesi. I don't know how to spell that. How do you spell? Khaleesi. How do you? Anyone know how to spell? Khaleesi. All right. Let me ask Google. Google, help me out here. Oh my gosh, I'm about to get spell corrected. Khaleesi. Got it. Ugh. All right. Oh my gosh. What happened here? Is that right? KH? Oh, I forgot the K at the beginning. Okay. I see. Yep. No one was named Khaleesi, and then all of a sudden, hundreds of babies were named Khaleesi. So if you meet someone named Khaleesi, you can probably guess that they were born in 2016, 2015. They're probably 4 years old right now. Yeah. All right. So let's take a step back now and kind of take a look at what we just did, or what I just showed you in this demo. How am I doing on time? Okay. So what I did here is I took a data set, I read it in, I did some manipulation on the data set, I looked at what was in my data by plotting distribution, and then I realized, oh, maybe I can do some more interesting analysis by bringing in a second data set. I brought in my second data set, I did some more manipulation on it, found some interesting patterns just in that data set alone, and by combining the two data sets, I was able to come up with a prediction for our particular class, or our particular data that I had here. We found out that the average prediction for age or sex distribution was kind of accurate, but probably not that accurate because we weren't using super sophisticated techniques. At the same time, it is kind of surprising that you can actually get some predictions that seem reasonable just based on combining some data sets about America with some data sets about this class. All right. And what I want to really highlight to you through this example is, okay, let me go back to my slides here. All right, so we've gone over this. And what I want to highlight to you is that data analysis is not just okay, I got my data, run a t-test, got a p-value less than 0.5, and call it a day, I'm good to go. Data analysis is really something that requires some critical thinking, a lot of times some creativity, and a lot of human judgment calls about whether your results are good or bad. And you'll find that's true in statistics as well, despite its intimidating math equations sometimes. A lot of times when we're working with data about people, when we're working under uncertainty, we have to make some judgment calls about what to do and what to do next. In this class, what we'll illustrate to you is what we call the data science life cycle, where we ask a question, obtain data to answer that question, understand the data, and usually what happens is we'll start perhaps either at the first kind of circle here or a second circle here. It doesn't always have to start with the first circle, but usually we'll start with one of the first two. In this case, for the names demo, I started at the second circle. We will understand the data, iterate, go back, repeat that process a few times, and try to understand the world by making some inference or making some prediction about the world. Using what we decide, we'll try to come up with some report, some product, some search engine, some face recognition algorithm. Who knows what we'll come up with. All right, and so you may also see this terminology being used to describe the data science lifecycle, where we'll say formulate a question, acquire and clean data, conduct exploratory data analysis, and draw conclusions or predictions or inference. Okay, I'm going to skip past these, but basically these questions kind of go into more detail about each step of the process. What I want to do now is talk about some course info, and we'll take a short break right afterward. So my name is Sam. My head TA's name is Manana. She was a student in my class a few years ago, and I remember the first day we were introducing ourselves in class. She was like, my name is Manana. And I was like, is that banana with an M? And she was like, yeah. And so I forever remember her name, and now she's my head TA, which is great. Okay, I have 4 teaching TAs who you'll meet later today, and 2 tutors who we'll talk about later. Okay, so about me, I'm currently a PhD student at UCSD. I work with a professor named Philip Guo on tools to help people learn data science. In the past, I was a student at Berkeley for my undergrad and master's. I TA'd for Berkeley 8 semesters total, so 4 years straight. And I was a TA for Data 8 its first 3 semesters, for 100 its first 2. I taught Data 8 for its summer offering 2 years ago, and I also wrote the textbook for Data 100. So I'm not actually you shouldn't call me Professor Sam, because I'm not a professor. You can just call me Sam. But I have been teaching this class for quite some time, and I do really enjoy teaching it. I hope that my enthusiasm makes it across in the class. I know this room is kind of big, so if you can't see me in the back, here's a big picture of my face. Okay, check our website. If you don't know that our website exists, you do now, and you should check it all the time, because all assignments, all lecture slides, all materials will be posted on this website. All communication through this class, when not done in person, will be through Piazza. If you're not enrolled in Piazza, please go to this link now to enroll. If you have a question on a homework assignment, what you should do is take out your particular solution from that assignment and post your question on Piazza. And the reason for that is because when you post on Piazza, other people can see your question, and if they have a similar question, they might also say that I had the same question. Or if someone has a solution for your question, they might post that on Piazza as well, saving you some time because you don't have to wait on me or the other TAs to kind of like go through our email inboxes and find your question. So try to use Piazza as much as possible. It'll make your life easier. It'll make our lives easier. It'll be a win-win for us. Okay. We have an online textbook for this class. It's at textbook.ds100.org. And it's a written resource for most topics that we'll cover in this class, although it won't be complete. It won't be like a comprehensive coverage, but it should provide, at this point in time, some supplemental material to help you understand what we did in class. Okay. Data 100 requires Data 8, or an equivalent class, 61A, which is the Introduction to Python Programming, and co-enrollment, or perhaps a prerequisite of linear algebra, of E16A or Math 54. So if you don't have these prerequisites, you may have some trouble with the class, since we won't go over in too much detail the topics that were covered in these classes. We will not be teaching you in particular how to use Python, how to use Jupyter, probability statistics, or linear algebra at some basic level. We'll just assume that you know it. I might do some quick review, but really, if you have trouble with homework 1, which is designed to be a test of your prerequisite knowledge, you should really consider coming back some other semester. Okay, grade breakdown from this class. You can check this on the course website. I just wanted to go over some quick reasons or quick rationale for this breakdown. Assignments are worth a lot of your grade, and that's because assignments are really important. They're important for learning because that's how you learn how to program, and pretty much like that's what you'll take away from this class when you walk out. We won't take any late homeworks from labs. We will allow late projects, but they'll have a penalty of 20% per day, rounded up to the nearest day, which means that if you turn in your project 2 minutes past the deadline, that'll be a 20% penalty. So please get your stuff on time. These policies seem strict, but the reason for that is because in the summer, classes move a lot faster than during the semester. So in the semester, we have 15 weeks to go over the whole class. In the summer, we only have 8, which means if you fall behind, you'll have a bad time, and that's no good for anybody. So please keep up with the class, and these policies are just designed to help you keep up. All right. In this class, we have a 5% grade allocated for attendance. Attendance will be taken using a Google form, although everyone gets credit for attending today. To receive that 5%, you need to attend more than at least 3 lectures a week for at least 6 weeks of the class, which is about 2/3 of all the lectures, which is not too many lectures. It's just meant to help you, like incentivize you to come to class. But if you can't make it to class for a particular reason, like you have a course conflict, I totally understand. And so if you don't attend lecture, the midterm and final will automatically be worth 2.5% more each. Okay. It's okay to collaborate in this class as long as you list your names at the top of assignments and don't copy code, don't copy solutions. The final exam is scheduled for 9:30 a.m. to 12:30 p.m. on Thursday, August 15th. That's the slot that we have booked for lecture plus the hour and a half afterward. If you have a conflict with the final, we have a conflict form for you to fill out, and we do have, I believe, one alternate final time from 12:30 to 3:30. So I think 61C, if people are taking that class, has an overlap with our lecture time and the final time, and because of that, we'll be doing some maneuvering to make sure you can take this class and take the final for this class. Okay, there's no alternate midterm time. The midterm, I believe, takes place Tuesday of week 4 of summer, although the exact date is on the course calendar on our course website. If you can't make that midterm, we won't give you an alternate midterm. Instead, your final will count for the midterm grade. All right. If you're on the waitlist for this class, there's no reason to be on the waitlist because we have open spots for you. So if you're on the waitlist and you want to be in this class, you should switch sections on Cal Central to one with open seats, and that'll get you into the class. Okay. Before I take a break, any questions about logistics? Yes?
Will there be a final project this summer?
Will there be a final project this summer? The answer is no. All right, so take a break.
There's a specific section on 1 through 10. Is it
Yes.
possible to get into it?
Sorry?
Is it possible to get into it?
If the section is full, you can only get in if someone else switches with you.
So even if there's like space there, like physical space, I can't get into it.
If there's physical space, you can attend.
Okay.
But like if there's no space in the class, then our policy is that our priorities for students enrolled in that class.
Okay.
Yeah. Hey.
Yeah, and I have not done any of the PLSC.
Okay.
And I was it's still possible,
Yeah, so it depends on your background. So if you've never programmed before, then you're going to have a hard time because we won't go over the basics of programming.
But do you think that if I work at home, everything is possible?
Anything is possible. It's just a matter of how much effort you want to put in. But I will say, look at homework 1. And if homework 1 seems impossible, like a monumental task, then you should really consider taking another class. We're taking Data 8 this summer instead of 100.
Okay.
Yeah. Okay. I will stay after class to take more questions. So yeah, please find me after class. I am a PhD student, working in like the cog-sci department on like human-computer interaction. Yeah. So.
Can you tell me more about that sometime? Or?
Yeah, sure. Come on me after class. Yeah. All right. Hello. Let's get rolling again. I know it hasn't been 5 minutes, but I did go a little longer than expected because I had too much fun with my demo. So let's get back into it, and I will try to end on time. Okay. What I want to do now is kind of give you a sense of why the life cycle, data science life cycle, is important, and also give you like a quick, a spark, a motivation or a spark to review some of the probability concepts you learned from Data 8. Okay. So I introduced to you that life cycle in the previous slide of the 4 steps. Ask a question, acquire the data, explore the data, and then make it inference and make a prediction. Each step of the life cycle has some problems when you do it incorrectly or don't do a thorough job of it. And in particular, if you're not careful about the second step of your data, basically errors that happen in one stage of the life cycle kind of propagate to all future steps, which means that if you have garbage data, you're going to make garbage predictions. In this class, what we call study design refers to the set of like guiding principles for data collection. We're going to talk about these principles today. I'll give you an example. So in 1936, a popular magazine was really good at predicting presidential election results. So they made correct predictions for 5 years in a row. Okay, so 1916 to 1932. In 1936, it was Landon versus Roosevelt, and they expected about 40 million people to show up to vote. So this magazine sent out 10 million mock ballots, and they got back 2.4 million of these ballots. Their prediction was that Landon would win by a landslide, by 57% of the popular vote to 43% for Roosevelt. And unfortunately, what happened is when it came down to the actual ballots, Landon only got 38% of the vote and Roosevelt got 62%. And this difference is huge. Now, this is like an error of like 20%, right? And so this is going from losing really bad to winning really bad. And to give you kind of a graphical sense of what happened, this is what happened. And what they did on the newspaper is like put it on like the New Deal spending $15,000 a night, turn this over and see who pays the bill, vote for Landon and Knox and end this extravagance. The other side was a pocket mirror. So you would kind of like the deal was like you look at yourself and be like, I'm paying for his bill, I should vote for Landon. And that didn't work out too well either. And what happened was, well, there are two flaws, right? The flaws were in data collection, not in their data analysis. One flaw is that the voters they sent ballots to were not representative of the electorate. So they sent out ballots to magazine readers. The magazine readers are not necessarily representative of the entire American public. The people who responded were also not representative of those who received the ballots, because people in general are more likely to respond when they're more interested or more passionate about something. So what you get is kind of like these bimodal results, where the most interested people who will vote yes respond, and the people who would strongly vote no respond. But you don't get too many people who will vote in the middle. You may also see this result happen in Yelp reviews, for example, or Amazon reviews, where you have like a lot of 5-star and a lot of 1-star reviews. And that's because of this phenomenon here, which results from basically giving people surveys to volunteer their answers to. Okay, and kind of the takeaway from this result and from other results in this class is that if you have a poor study design, you're going to get some biased results. And you may ask the question, well, why can't they just keep collecting more data? If I just have all the data, won't my results be 100% accurate? And the answer is yes and no. In this paper published by some statisticians at Harvard, it's a fun title, which is the only reason why I include it. It says, I got more data, my model is more refined, my estimate is getting worse, am I just dumb? And the first sentence of this paper is like, possibly you are. But more likely you're merely the victim of conventional wisdom. And conventional wisdom is that if you collect more data, your results will get more accurate. But that's not necessarily true. The reason why it's not true is because there's different kinds of samples, and different kinds of samples let you make different conclusions about your data. First of all, you may have heard the term census. A census is just all the data that's possible to get about a particular population. So for example, the US Census collects information about everyone in the US. Of course, they don't get every single individual in the US, but they get pretty close. And for that reason, for most purposes, we consider the US Census a census as well of people living in the US. In this class, however, and in real life, you'll mostly be working with samples, which is a subset of the data, rather than the entire data set at hand. In particular, if you have a census, you don't have to do prediction, you don't have to do like estimation or prediction techniques. If you have a census and you want to know the average age of a person in the US, you can find that age, and you'll know that age exactly because you have access to all the data about everyone in the US. If you only have a sample of data, like 100 people from the US, then you'll have to do some statistics and you have to do some modeling in order to figure out what to do. In particular, if you have a census, for example, there's no reason to make a p-value or a confidence interval because those are probabilistic methods, and those don't apply when you have a census of everyone in the US or everyone of your population of interest. there are different types of samples: self-selected samples, convenience samples, judgment samples, administrative data sets, and the most important sample of all, perhaps the probability sample. The difference between the first 4 samples and the last type of sample, the probability sample, is that the first 4 samples are kind of like taking people arbitrarily, but the last type of sample is taking subjects or individuals at random. Arbitrary and random are not the same things, because in the probability sample, you must be able to assign a probability to every subset or every possible sample you can achieve. Okay, there are many types of probability sampling, but we won't go over them in this class. Instead, we'll stay in the land of the simple random sample, which you may remember from data 8, which is a sample drawn uniformly at random without replacement from a population. Let's try some problems. Suppose we have 6 people, and we just give them the first 6 letters of the alphabet, and we take a simple random sample of size 2. What is the probability that A is in my sample? And what is the probability that C and D are in my sample? Why don't you talk with your neighbor for 3 minutes, try to come up with the answer, go. All right, so I hear some talking, which is good. I see some thinking, which is also good. This problem is kind of a warm-up problem for you guys, so let's take a look at how you can solve it. This one way to solve it is I heard people talking about like multiplication and doing some additions. That's a good way to do it. For a problem this simple, what I can do is I can just write down all the possible samples of size 2, there are 15 of them, and then I say, okay, well, the probability of getting C and D is 1 possibility out of 15 possibilities, so the probability of that happening is 1 over 15. The probability of A appearing in my sample is I just count up all the ways of A appearing, which is the top row, which is 5 possibilities. Out of a total of 15 possibilities, 5 over 15 is 1/3. So probability of A is 1/3, probability of C and D is 1 over 15. The other way of doing this problem involves knowing that, for example, to pick A in your sample, A has to be either the first person in the sample or the second person in the sample. And so the probability of that happening is a probability of picking A first and then some other person second, or a probability of picking some other person second and A second, or a probability of picking some other person first and A second, and adding those probabilities together. But we'll get more practice with that in probably this next example here. So we have 2 classrooms. One is called D8, and one is called D100. D8 has 10 students, none of whom are named Sam. D100 has 4 students, one of the students is named Sam. Suppose we do the following. So we flip a fair coin to pick a classroom. So we either pick D8 or 100, and then we take a simple random sample of size 1. What's the probability of picking D8 given that Sam was in my sample? And what's the probability of picking D8 given that my sample did not contain Sam? Okay, so why am I being interested in these questions? Well, sometimes we're taking a sample and we want to figure out, based on my sample, where did my sample come from? So we have some like rats together, or we have some rats in our lab, and all of our rats died, and we're like, oh my gosh, where do we get our rats from? We never want to order from this lab ever again. And so in this case, what we want to do is take our sample and use the sample to infer what population it came from based on some data. And in this case, what we're trying to do is infer the classroom that I picked based on whether Sam was in my sample or not. Why don't you think about this for 2 minutes, talk with your neighbor about it, see if you can come up with something reasonable for these two problems here.
What's the probability that is there?
How many of you guys are still working on this? Show of hands. All right. If you got the answer, 1 for a second question here, you flip the given. Okay. So if you got the answer 1 for this one, you probably computed probability of getting no SAM given D8, because that's the reasoning of if I picked data 8 does not have any SAMs, so the probability of getting no SAM in a sample is 1. That's the example of a choice I would definitely give on a multiple choice test. Okay, so just keep that in mind. You don't want to flip these givens. They're important. They're important in the order that they are. Okay, the first question, probability of D8 given SAM is 0, because we know that data 8 doesn't contain any SAMs. So if SAM appears in my sample, we know for sure that the sample was not drawn from data 8, it was drawn from data 100. Okay, so that one was not too bad. The second one is a little more complicated. Oh man, my animations got messed up. Can I fix this? All right, fix this. Let's do that, fade that in. Let's do that, fade that in. I don't want to scare you guys with this just yet. All right, okay, cool. And so to find a probability of picking data 8, given that my sample did not contain SAM, what I do is I apply Bayes' rule. Bayes' rule says that the probability of the left-hand side is equal to the probability of picking D8 and no SAM over the probability of picking no SAM at all from anywhere. Okay? So we can calculate the numerator and the denominator separately. The probability of the numerator is the probability of picking D8 and picking no SAM. The probability of picking data 8 is 0.5 because you're flipping a fair coin. And the probability of picking no SAM is 1 because data 8 does not contain any SAMs. Okay, the probability of picking no SAM, we have to split that up because we don't actually know that probability. So the probability of picking no SAM is the probability of picking D8 and no SAM, and the probability of picking data 100 and no SAM. I add those up to get back the probability of picking no SAM. And so I can calculate each of these individually. The first one is 0.5 times 1, the second one is 0.5 times 3/4, and I get 7/8 as this total probability. So what I do in the very end is I say, okay, here's my numerator, 0.5. Here's my denominator, 7 over 8. And I just take 0.5 over 7 over 8, and I get 4 sevens. Okay, so that should scare you, and that was meant to scare you. If this looks totally unfamiliar to you, then you might not have the probability prerequisites for this class. But if you're taking data 8, you may have noticed that we use Bayes' rule at the very end of class. And so this is kind of a reminder to you that you should go back to data 8 and review some probability. There's an easier way to do this problem without working with all these probabilities. The easier way is to draw a tree. Okay, we draw a tree. We notice that the first step in this process is to pick either data 8 or data 100. Each of those happens with probability 0.5. After we pick data 8 and 100, we have 2 possibilities after that. One possibility is our sample contains SAM, and the other possibility is that our sample doesn't contain SAM. What I do next is you can say the probability of picking SAM given data 8 is 0, and the probability of picking no SAM after picking data 8 is 1, because data 8 doesn't contain any SAMs. For data 100, 1 out of the 4 students was named SAM, so the probability of the top branch is 1/4, and the probability of the bottom branch, by definition, is then 3/4. So, the probability of picking data 8 given no SAM is looking at the branches that have no SAM, which are these 2 branches. Which of those branches correspond to the possibility of picking data 8? Dang it, I drew that box in the wrong spot. This is some last minute editing. All right, that's a little better. All right, let's try that. Okay, so the given says, look only at the branches that end in no SAM. The part before the given, the part of data 8 says, look at the branch corresponding to data 8. And so what I do is I say, okay, the answer to this question is the probability of the orange box divided by the total probability of the blue boxes. I look at the orange box and I see that this branch's probability is 0.5 times 1, so I get 0.5. The probability of the blue boxes put together is the probability of, I'm going to do this, 0.5 times 1 for this top blue box, and then 0.5 times 3/4 for this bottom blue box. I add them together to get the total probability of the blue boxes, and I get the same equation that I got before, just in a graphical way instead of using a bunch of equations, and I get the same answer. Okay. So if that was scary to you, I know it has probably been a while since you've taken data 8, but you should review these chapters from data 8 in preparation for homework. Homework 1 asks you a question about Bayes' rule, as well as for the rest of this class, because we'll be using those probability concepts pretty soon to talk about some more sophisticated things involving samples. But for today, the reason why I'm trying to remind you guys to review some probability is because probability plays a really important role when it comes to sampling. Here's the reason why. So the question we asked before was, if we had tons of data, won't our results always be good? The answer is yes if you have a census, but probably not if you don't have a census. And what we can do is we can kind of compare 2 samples. Okay, so in 2012, we had a presidential election, and let's suppose that we're trying to predict the results of that election. Now, we can compare a simple random sample of 400 individuals from America, or we can compare a non-random data set, an administrative data set of 60 million individuals with a 1% bias. Okay, so what we have here on the top is a small sample, but it's random, okay, which means that every person in the US was selected with equal probability. Okay, so that's the important thing to take away from this. The data set on the bottom, we cannot assign probabilities to people appearing in our sample, but we do have a lot of data. We have 60 million people in our sample, and we know in 2012 that there were 120 million voters. So this sample here, which is probably like a bajillion, no, not a bajillion, it's probably like 10 times as big as like the actual, like any survey you'll ever see in the real world. it has about half the US in the data set, and it has a 1% bias, which doesn't seem like a whole lot, okay? The spoiler here is that the SRS, the simple random sample, wins. And what do I mean by wins? I mean this. When I take my simple random sample and make a confidence interval from it, which means that from data 8, I will bootstrap that sample and come up with a bunch of different sample proportions, okay? And I do the same thing for a large administrative data set, and I plot the true proportion of voters, so voters for Obama, on the red line here. What you see is that although the simple random sample distribution is very wide, the confidence interval for this particular sample will contain the true value, the true proportion of Obama voters. The big sample, on the other hand, will have a very narrow confidence interval, right? So this confidence interval is actually much narrower than what you see here. It's just because of the binning that I use that looks like a big block. But you can imagine that this confidence interval would only span like maybe a 0.5 to 0.51 or something like that. It will never contain a true value. It will always be wrong. Whereas a simple random sample will be pretty wide, but it will at least be right sometimes. It will contain a true value sometimes. And in particular, when you have non-random data, what happens is as you get more data, and because your data are often biased, inherently in a non-random sample, when your data set size increases, you get more certain about the wrong answer. So what's going to happen here is that if I take this non-random sample, the big administrative data set, and I just keep collecting more data, right? I keep collecting more voters. This interval here will just keep getting narrower at the bias, around the bias. It'll just get worse and worse and worse and worse until I get to maybe like 95% of the US, and then it will kind of shift over to the true value because now I'm collecting everyone in the US. But really what's happening is non-random data are often biased, and because they're biased, as you collect more data, you get a more precise answer, but not necessarily a more accurate answer. Whereas if your data were collected truly at random, we'll go over techniques in the class later that show you that a random sample is unbiased, which means that even though your sample may be small, you'll at least get an answer that's reasonable. You can at least create a confidence interval from your answer and know, for example, that if you create a 95% confidence interval, that if you take a bunch of samples and create a bunch more confidence intervals, that the actual proportion of Obama voters is within that interval. For that administrative data set, if I had a bunch more administrative data sets, their quote-unquote confidence intervals will never contain a true proportion of people who voted for Obama. And in that sense, that it's kind of what I'm trying to show here is that techniques you learn in statistics, like p-values and confidence intervals, don't really apply to non-random data, because for the assumptions underlying p-values and confidence intervals to actually have meaning, you need to be able to assign probabilities to your data, and in non-random data, you aren't able to do that, and because of that, p-values and confidence intervals don't really have too much meaning unless you make some hard assumptions there. Okay. In summary, data science is important, the data science lifecycle is important, and taking a random sample is better than a non-random sample. Thanks, and I'll see you tomorrow.